where people have sort of used robots to do these inspections.
These sensors will be very quickly able to tell you.
So very interesting that we left it for curing.
Good evening, everyone. I, Shivangi, the moderator for today's session, feels privileged to extend you all a very warm welcome on behalf of the CES Club of NIT Rourkela in collaboration with IC UK, NIT Rourkela chapter, who has clubbed us all for another brand new session of CIVINAR, where we welcome eminent personalities from different fields of civil engineering for highly intuitional webinars. Our previous sessions were graced by Professor Sriram Narasimhan from the University of Waterloo, Canada, Professor Nemi Banthia from the University of British Columbia, Vancouver, Canada, who is also the Scientific Director of IC Impacts Canada, and Professor Rishi Gupta from the University of Victoria, Canada, who gave their valuable insights on the different fields of civil engineering. Now, without further ado, I would like to call upon Mr. Armandev Puhan, Organizing Secretary of CIVINAR, for a welcome address.
Hello everyone. As the winter sets in, a warm evening to all of you present here. I am Armandev Puhan, Treasurer of CEST Club of NIT Rourkela and Organizing Secretary of CIVINAR. CIVINAR is an online webinar come talk session organized by CEST Club of NIT Rourkela in collaboration with ICE UK NIT Rourkela chapter. It is hosted by YouTube Live platform. The purpose of CIVINAR is to provide the entire civil engineering community with a diversified platform to gain and share knowledge about certain topics of current and future interests in the field of civil engineering by noteworthy personalities who have attained expertise in their respective domains. This evening, from our institute, we are joined by Professor Samuel, Assistant Professor from the Department of Civil Engineering of NIT Rourkela, with a specialization in structural health monitoring. Thank you, sir, for joining us tonight. As mentioned by Shivangi, distinguished professors from all over the world have graced our seminar. Adding another feature to our crown, today we are joined by esteemed Professor Ayan Sadhu from the prestigious Western University of Ontario, Canada. I feel proud and privileged to welcome Professor Ayan to today's session. It's quite an honor to have you with us, sir. Last but not the least, I welcome all the audience members to today's session. Without your valued and continued support, CIVINAR would not have flourished. Thank you so much for joining. Shivangi, over to you to continue the session.
Thank you, Mr. Armandev. Now I would like to request Professor Shyamal, Associate Professor of Structural Engineering from our institute, to say a few words on today's auspicious event that we are delighted to host.
So thank you, Shivangi. From my bottom of my heart, I welcome Professor Ayan Sadhu on this CIVINAR talk. Actually, he is a very eminent academician in the field of structural health monitoring, and he is currently now assistant professor in Western University, Ontario, Canada. And before to that, he was assistant professor at Lakehead University from 2014 to 2018. And he has done his PhD from University of Waterloo in 2013, and before that he has done his MTech from Indian Institute of Technology, IIT Kanpur, India, and completed his BTech from Jadavpur University, India. Basically, his research field is structural health monitoring and condition assessment of structures, damage detections and pattern recognitions. And presently, he is involved in research in theoretical as well as experimental in the field of damage detection and structural health monitoring. He has published a lot of journal papers in ACI and in very well-reputed journals like Journal of Sound and Vibrations, Smart Materials and Structures, Journal of Computing in Civil Engineering, ASCE. Okay, so this list is very large. So and he is a member of different professional societies like member of Professional Engineers Ontario PEO, member of American Society of Civil Engineers, member of Canadian Society for Civil Engineers. He has done a great achievements in this research field, and he has different awards and achievements on his name. He has served as a guest editor in Frontiers of Building, Built an Environment in Structural Sensing, Reviewer Award for the International Journal of Smart Materials and Structures. Dr. Sadhu research was funded by NACRC Discovery Grant in 2015. He has received the Doctoral Thesis Excellence Award from the University of Waterloo in 2013 and received gold medal from IIT Kanpur in 2007 for excellence in graduate studies. So I welcome Professor Sadhu to deliver his talk on the topic of failure assessment of structure. So Professor Sadhu, please.
So can you see my screen? Hello, can you see my screen?
Yes, sir, it's visible.
Okay, that's good.
Excuse
Okay,
me,
thanks,
sir.
Yes.
Sir, a small housekeeping for the audience. If anyone has any questions during the webinar, they may type it in the live comment section, as there will be a question and answer session followed by this webinar. Over to you, sir.
Okay. So since my screen is full screen, so maybe I not be able to see the chat box question, but maybe you can just stop me during the presentation and I'd be happy to respond to the question. Okay, Dr. Samuel, thanks for your excellent introduction about myself. So those, and again, thanks for giving me this opportunity to present my research in front of you. I hope all of you are doing well during this pandemic situation. And especially for the students, it's really challenging time because you guys are taking online classes and missing the key component of engineering education in the university campus. But I think this seminar is really a valuable opportunity for you to get into touch with a lot of research components from different other universities. So today my presentation topic is technology-enabled structural health monitoring of large-scale structures. And I think Dr. Samuel has already mentioned a short bio about myself. So basically, I did my bachelor's from Jadavpur, and I'm originally from Calcutta. And then I did my master's from IIT Kanpur, and then I worked in General Electric Aviation for 2 years, where I was involved as an vibration engineer, worked in General Electric. So basically, I was involved in finite element modeling and dynamic analysis of engines, aircraft engines. And then I decided to come to Canada for pursuing my PhD in structural engineering. I came to University of Waterloo. I spent there maybe 3.5 years. I completed my PhD, and then I was a postdoctoral researcher for 1 year. And immediately after that, I got a faculty position at Lakehead University, which is in Thunder Bay in Canada, which is basically very close to Lake Superior. As you know, in Canada, we have the Great Lakes, and Lake Superior is one of the largest lake in the world. And Thunder Bay is basically very close to Lake Superior. And after spending 3.5 years there, I moved to Western University in 2018. And so basically, this is Western University. As you can see here in this slide, the iconic structure. So most of you who comes to Western campus, they actually at least take a picture with this iconic structure. And you can see the campus is very nice and beautiful. So let's see a slide on Western University. So basically, where is Western? So Western is located in London, Ontario. It's not in London, UK. It's in London, Ontario. And this is one of the oldest university in Canada. As you can see, it was founded in 1878. And it was previously known as University of Western Ontario. And recently they changed their name to Western. But we have nearly 40,000 students. So it's a huge university. We have different faculties starting from engineering, science, social science, and various other faculties. Also, it ranked #1 in Canada and ranked 13 in world under the category of civil engineering by Shanghai ranking. So it's very reputed university. And Western also basically it homes to some of the world-class wind engineering labs like boundary layer wind tunnels and windy facility. Now, those who doesn't know windy, maybe you can take a quick search in Google later on. Windy is basically a stadium-sized lab where we can simulate tornadoes and hurricanes to see the effect of damage in the buildings or bridges. So a lot of iconic structures, they are actually designed in this lab in the past. So that's a brief about Western University. And so basically today my presentation outline is this. So first I'll give some research background about myself, followed by an introduction of structural health monitoring. And then we'll talk about the artificial intelligence, how we can use this as an eminent technology for structural health monitoring. Then we'll talk about some of the methods that we have developed so far, followed by some full-scale validations. And then finally, I'll conclude with some of the main summary of my presentation. So basically, infrastructure monitoring is really important in the context of today's world, because most of the structures, they are actually aging. And because of the aging, it may have damage or it may have anomalies. So it's very important we detect those damages at the early stages such that we can prevent the catastrophic failures. So that's why infrastructure monitoring is something like we collect data from the structure and we make the decisions. Okay, so that's why I say this as data to decision. In short, we can say as D2D. Okay, so what is D2D? D2D is basically making data, getting data, and make the decisions. So under this framework, there are multiple avenues of research. So first of all, when we say data, that means we need to do some sort of condition assessment using dynamic testing or monitoring. So usually we put the sensor in structures like bridges, buildings, dams, and we get the valuable data. Now the next step is how we collect the data. Definitely these are collected by sensors, but sensors are advanced now. It is not just like visual inspection. Nowadays we have wireless sensors, we have camera, we have acoustic sensor, drones, and passing vehicles. So these are different types of sensors that can be used for monitoring purpose, and that involves research as well. Now, once you install the sensor, we get data, but that data could be really big because we may talk about data collection for few days or few weeks or few months. So it will result into a huge chunk of data. So how can you manage that data? So to management or better visualization of the data, there are different techniques available. For example, building information modeling or virtual or augmented reality or different artificial intelligence technique. And that's why one of my research is also involve how we can analyze this big data using different techniques. Now, let's say you get the data now. Now we need to basically identify some of the hidden information from the data. And for that, we need to do some system identification. And that's another one of my research contribution, where we develop different methods like time frequency domain methods or signal processing or pattern recognition kind of methods, such that we can identify the hidden information about the structures from the data. And let's say you make the right system identification, and then you come up with the decisions. So what would be your decisions? You may say, let's do the retrofitting of the structure, or let's do the maintenance of the structure. So when we say maintenance, we may come up with some intelligent systems. For example, we may come up with a nice design for tune mass damper, or maybe we can come up with some automation. So that's why you need to design some intelligent system, and that's one of my research area as well. Also, we can come up with some decision about, let's say, after how many years we need to do the maintenance for that bridge or building. So that is something like remaining useful life, which is also known as RUL. So sometimes, based on the data that we collected and the decision we made, we can say, let's say after 2 years we are going to do the maintenance or retrofitting, or maybe we need to do the retrofitting immediately to prevent the catastrophic failures. So we can make those kind of decisions, which involves a lot of statistical analysis. For example, different Markov models or random vibration theories to basically understand the statistics of the data and make the decisions. So this is in general all of my research areas, and my team, many students, they are working on item A, B, C, D, E, or F. So that's what I basically see my research contribution in this field. So with this research background, let me quickly introduce you with the structural health monitoring. So especially for the students, like undergraduate students, I think this slide tells you what does it mean by this buzzword structural health monitoring. Now, recently we have seen a lot of failures in different structures. For example, Nipigon Bridge, this is actually a new bridge that was built in 2016 in Ontario. And immediately after the failure of this bridge, immediately after the construction of this bridge, there was some failure, and it was stopped for the public, and then it was reopened. Then there is another example here, which is in Alberta. There was a significant flood, and there was a failure in the foundations. And you can see there are other failures in some of the bridges in US because of the natural disasters. And these are not the single examples. There are numerous catastrophic failures worldwide. As you can see, this is apartment tower failure in China. Then there is a bridge failure in US, dams and mine failures. So this kind of failures are primarily due to the natural disasters or structural aging. It may be due to the deferred maintenance or faulty constructions. Now, if you look at the America's GPA, so this is same as like your report card. So every year or every 2 or 3 years, America's infrastructures, they are inspected, and we come up with some sort of ratings like your report card that you have at the end of every semester. So we say, what's the status? And you can see that as per ASCE's, as you know, American Society of Civil Engineers, as per this organization's report card in 2017, America's GPA is D+. So you may notice that we are not doing well. Our infrastructure is having a rating of just D+, which is not good. Same kind of observation we also have found in Canadian context. For example, CSCE, which is the Canadian Society of Civil Engineers, Civil Engineering, as per their 2019 report card, they clearly stated it's a good idea to pay a penny now rather than spending $1 later on. So both of them convey the same message, that the infrastructure wise we are not doing well and we need to improve that process. Okay, so fortunately structural health monitoring gives a powerful solution to this problem. In the context of structural health monitoring, structure is like a human being. So like any human patient, we put the sensor in the structure and then we collect the data, and based on that we see what's the condition of the structure. Okay, so that's why we say this as structural health monitoring. Okay, I hope with this the idea is clear now. Now let's see what are the components of structural health monitoring. So first is the data acquisition, where we actually put a lot of sensor. We need to come up with what should be the ideal location of the sensor. We cannot just say randomly put the sensor in different location. That's not possible. Also data fusion. So sometimes we may use sensors like accelerometers. Sometimes we also use the strain gauges or displacement meters like LVDTs. So we need to come up with what should be the proper combination of the sensors such that we can get the best quality of the data. And another important thing is we need to also make sure we collect data remotely, because sometimes it is not possible to manually put the sensor and get the data for a few days or a few weeks. So sometimes we need to do that remotely as well. So there are a lot of challenges. Now, once we get the data, the next step is system identification. System identification means to identify the hidden information about the structure from the data that are collected. So that involves some sort of signal processing. Now, once we know the system information, the next step is the damage assessment. So what is damage assessment? This is where we try to find out what should be the location of the damage or what is the severity of the damage. So sometimes just there is a damage, that doesn't mean that we need to do the repair. So the damage could be very minor, so we can leave it or make any kind of future decisions. So that's our last step to make the decisions whether when we can do the inspection or rehabilitation or maintenance. Okay, so in my research, we try to develop different diagnostics or prognostic techniques to improve the existing SHM techniques. So let me show you what actually mean by system identification. So let's say this is maybe a civil engineering structure. As you can see, maybe a 3-story building. And let's say this is subjected to some load by wind or earthquakes or man-made excitations. So we can represent this picture using this schematic. Let's say this is the input, which is wind, earthquakes, or man-made excitation. And then this we have the output, which is maybe the response. Maybe this is the acceleration response or displacement response, right? That's what we know from engineering, civil engineering studies, that if we apply input, we'll get output, and that output will contain the measurement that we can measure from the structure. Now the question is, can we identify the hidden information, which may be the frequency response functions or impulse response functions? So these are actually important information about the structure. Okay, and if we identify them from the input or output, then actually we can say what's the condition of the structure, right? And that's why it is also called inverse problem. Why inverse problem? Because here we don't know this, like the structural property, we only have output, and based on the output we need to go back, or basically we need to go backward and find out this, right? So that's why it is also called inverse problem, because we are finding the main information about the structure based on the output, not from the input. Okay, so that's why it's inverse problem. Now, what are the advantage? This kind of informations, they are extremely important for diagnostics and prognostics, and also to design different control devices, for example, tune mass dampers, that I'll talk about maybe slightly in our upcoming slides. And these are also good for prediction. For example, let's say you design a new building or bridge, you can say with this kind of information that what would be the response under some hurricanes or tornadoes. So you can make those kind of decisions. Okay, so that's why these are very important. But there are many challenges because structural health monitoring is not new. There are development for last few decades, but there are still many challenges. For example, when we say the excitations, for example, the excitations could be wind, earthquakes, or different man-made excitations. They are actually either narrowband or wideband. So depending on the statistical characteristics, they could be anything. So performing system ID or system identification will be a challenge. Also, these are non-stationary. So when the excitation is non-stationary, there is a significant challenge to perform the system ID using traditional methods. Also, when there is a damage, our system becomes time varying. So for time varying system, damage identification is not that simple. Another common challenge is the limited number of sensors. So because of the cost, the labor cost, or the time that are required for installing the sensor, it is actually huge in terms of cost analysis. So we need to always make sure how we can optimize this instrumentation using limited number of sensors. So when you say limited number of sensors, that means we are trying to extract the information based on the few sensors. So that is another challenge. So in my research, as you will see in next couple of slides, that we develop different artificial intelligence technique to solve this kind of challenges in a systematic manner. So let me introduce briefly with artificial intelligence. Artificial intelligence is something is very like well known now. It's a buzzword, as you probably all of you know, starting from the smartphone up to say the autonomous vehicles. Everywhere we see artificial intelligence. Even in Facebook, YouTube, when you search a video, when you type something using this kind of AI techniques, you can see the best possible search depending on your keywords, right? So this is very popular nowadays, and there is a lot of development in this area. Now let's see what is artificial intelligence. So basically, it is something like you are applying the human intelligence and you are automating that into machines, right? Or in computers, such that computer can do exactly same way as a human can do. And there are basically two different branches. One is called the machine learning, another is called deep learning. Now machine learning is basically something which is relatively well developed and established, whereas deep learning is something that has been developed in last few years. So this is very new, and there are significant development in this area nowadays because of the computationally efficient computers that we have nowadays. Previously, it was not possible because we didn't have GPUs or high capable computers. Nowadays, because of the high performance computing or the graphic processing units, nowadays it's very easy for us to perform this kind of exercise like deep learning. Now, we are civil engineers. Definitely some of you may say, okay, how can we implement this, or what's the point of talking about this in civil engineering domain? Now the thing is that civil engineering is not just concrete or steel structures. At the end of the day, when they age, we get the SHM data. Now as soon as we have data, that means we need to analyze that, and then we need to basically use some sort of advanced techniques to analyze that data and make sure we identify the correct information. And that's where this kind of advanced technology will help us. So don't think that civil engineering is all about reinforced concrete and steel design. you will soon see that there are a lot of advanced technologies nowadays. And as a civil engineer nowadays, I think this is one of the most important engineering topic, where we are actually encompassing our knowledge in different areas. And this is a perfect example where we are applying machine learning or deep learning into civil engineering domain. Now let's see what is machine learning. As you can see here, this is where we can do global damage identification. That is one of the advantage. Also in machine learning, we can use limited samples of data, which is good because we don't have to bother about a large data set. And these are very fast and efficient. So that's another good news about machine learning. But there are a couple of drawbacks. What are the drawbacks? One of the first thing is it requires feature selection. So if I give you some data, you need to basically identify some important feature out of that. Otherwise, you cannot do anything. And that feature selection needs a lot of training. Okay, so that's one of the challenge, especially if you want to deliver a technology and give it to some company, industry, then they may not be aware of those kind of features, and that would be difficult for them. So it is not that automated process. And then also it requires dense instrumentation. So that means if there is a structures like buildings or bridges, we need to put a lot of sensor. So that means it would be very expensive. And at the same time, it can use only the time series data. So it cannot use like images or videos. Okay, so that's a couple of drawbacks. Whereas in deep learning, there are a lot of good news. For example, it can do not only global, it can also do local damage identification. So that's good because let's say if you want to detect the damage in the connection, which is very localized event, so we can do that. At the same time, it can analyze very few measurements, which is really good. You don't need a lot of sensing. Another good thing, it can actually use time series, images, or videos. So we don't have to just rely on time series. Even if you capture or take images from camera or videos, then we can also do the data processing using deep learning techniques. And it is free of any feature selection, which is actually extremely advantageous for us because we don't have to identify a feature like machine learning. But there are definitely some drawbacks. For example, to do this, implement this process in our data sets, the data should be big enough. So that means we are talking about huge data set. And we need computing facilities, but definitely it is not a challenge nowadays because in most of the universities or industries nowadays, we have high performance computing. So GPUs will not be a big deal for us. Now let's see what does it mean by blind source separation. As I said here, that machine learning is one sort of pattern recognition method. And in my research, I developed blind source separation type machine learning technique to perform the system ID. So what is blind source separation? In simple way, we can say, let's say there were two speakers. Okay, so suppose there were two speakers and there were two microphones. So each microphone is receiving sounds from these two speakers. So the question is, can we separate the individual sound from this microphone data? So that is called blind source separation without knowing anything about the physical mixing. So this is why it is called blind, because we don't know anything about A, which is the mixing, but we still would be able to separate the signals out of these two original sounds. So we basically use different statistical characteristics of the signal, and definitely I'm not going into the details of it. Those who would be interested, you can see my publication here that I showed, and that way in future you can develop a good understanding on that. But maybe I'll explain what's the significance of blind source separation in the context of civil engineering. Now let's say, think about a bridge. If you want to monitor a bridge, and when you collect the data, you may expect that this data will contain the responses due to the moving track here, due to the trains passing below the bridge, and also the different operational conditions. So for example, we may have different responses from different systems. So at the end of the day, whatever data we collect, this is basically a mix of multiple signals, right? So this is very same as here, where the mic contains a mix of individual signals. So this is very same situation as here. Similarly, if you think about a building, if any of you has taken structural dynamics, probably you know that building response is basically a mix of multiple modal responses, right? So the measurement also contains the mix of modal responses. If you think about a dam basically, if you think about the measurements that we have, let's say seepage or uplift pressure or strain displacement, they basically contains the response from the combination of temperature, water levels, age, or earthquakes. So at the end of the day, what we can observe is our measurement contains the sources from different multiple sources like the traffic or temperature, water levels, and so on. So the main problem is basically same as here, where the measurement contains multiple sources. So that's why you can say we can use the BSS or blind source separation to separate them out and identify the most appropriate signal that contains the damage information about the structure. So that's one sort of technique. And another kind of technique called convolutional neural network, which is part of deep learning technique. Again, I'm not going into the details of it, but in simple way, we can say this contains a series of multiple layers for pattern recognition, such that if we give some input, it will identify the features or the output at the back end. And the advantage here is, as I said, for the deep learning, we can use either time series or images or videos. So that's one of the advantage for us to analyze different deep learning techniques. So in my research, I used blind source separation or CNN for structural damage assessment. So without any further background, let me move into some of the methodologies that we have developed so far. So as you know, there has been significant development in sensing technology. For example, 10 years ago, people used to use, say, sensor accelerometers that are installed in a bridge deck, and we get the measurements. Whereas nowadays, we are using unmanned ground vehicles or the smartphones or the drones or cameras. So if you realize the basic difference between the traditional sensor and this sensor, what do you think? You can clearly see that these sensors, they are actually very localized. So they cannot have the measurement for the entire structure. So if you think about the drone, it is focusing only a particular portion of the bridge. Or if you look at the smartphone, they are measuring only one portion of the bridge or the structure. So we can say the data collection is decentralized, which means we are actually measuring data only from a limited portion of the structure, and then we are moving into another location and we are finding another set of measurements. So the basic problem or the challenge here is we have limited number of sensors. So in my research, we developed methodologies to identify the structural damage using limited sensors. And for that, we use sparsity, the concept of sparsity. Now, what does it mean by sparsity? It is very simple, and I hope this picture is will be very clear. So let's say this is two sine signals. This is sine signal 1 and this is sine signal 2. And then I mix them and I am showing this in time domain. So here you can see this is not giving any information whether we have two sine signal or not. But now in this picture, I'm showing this in the frequency domain. And here now the interesting thing is you can see there were two clusters, right? And why there were two clusters? Because we have two sine signals. That's why we can see there are two clusters here. So this is called sparsity. So what does it mean? It means that if you transform a signal from time domain to frequency domain, we can actually classify or make two different or three different clusters corresponding to the original hidden signal. So as soon as we do that, we can say, okay, the data contains two sign signals or three sign signals and so on. So then if I use inverse frequency domain transformation, we should be able to get back the original signal that we mixed at the beginning. So that's the advantage. We are actually going back from the backward, from the end to the front. So we are solving the backward problem. So with this, we are able to find out the hidden information about the structure, and that is very beneficial. Another challenge that we have solved in my research was how we can find the closely spaced frequency. So let me give you a nice example. So in this picture, you can see this is a TMD. What is TMD? This is called tune mass damper. So why we need that? Let's say we have a tall building like this. Now for the tall buildings, it is very flexible, right? If you think about your final year course, or where we talk about the stiffness method of structural analysis, as you know, if a structure has too much height, then what happens? The structure becomes flexible, so it becomes it will cause a lot of displacement on top, right? So if you think about this tall building, if it is too flexible, then it will have a lot of deflection on top, which may not be good if you are on the top floor, right? And this is in single TMD, or the tune mass damper. This is actually very popular. So it is actually installed on the top level of the building, such that if the building moves in this direction, it will move in the opposite direction. And because of the out of phase movement, it will reduce the vibration level. So that's the advantage. So this is called control devices. And this is a typical tune mass damper in type A 101. If you search a Google with TMD in type A 101, you will see a nice video, and you will see how people actually can go there just to look at this TMD. This is actually a huge weight which is suspended on top level of the building. Now this is like TMD, but what's the challenge here? Let's say with time, let's say after 20 years of installing this TMD, we may expect that there is a change in the property of the structure. So because of that, what happens? There may be some changes, and these TMDs get detuned. As soon as they get detuned, what happens? It will not serve well. So that means the top level may not be having smaller displacement, it may have larger displacement. So that is not good, right? So let's say you are eating on the top floor. Let's say there is a restaurant, and if you're eating there, because of the wind, you may see a lot of vibration. So what's the solution? That means we need to do the retuning of those TMDs. We need to fix the TMDs, right? And to do that, we need to do system ID. Now, what is the challenge? This is a lab model of TMD. You can see this is a small scale TMD which is suspended on top. The challenge is here. So this picture is basically a frequency domain information, and you can see the frequencies. These peaks are nothing but the frequency of the building, and you can see there are two closely spaced frequency which are very close. And if we use traditional method, it would be very difficult to separate them, and without a good separation, we will not be able to do anything. So in my research, we develop some mathematical tools by which we can separate them, and we can perform the right system identification. Then structural damage detection is another challenge, and this picture I'm showing you a couple of mathematical or signal processing tools by which we can detect the damage. For example, here this is like a discrete damage. Sorry, this is some discrete damage that we are trying to identify. This is some sort of progressive damage, as you can see. So with this kind of signal processing tool, we have been successful in identifying the damage in the structure, because whenever there is a damage, structure becomes time varying. So for example, here, this is again some sort of signal processing information that shows that the frequency here is reducing because of the damage, right? So these are nice way to see what's the progression of the damage. So this is another example where you have used a tool like wavelet transform or wavelet transformation of the data. And here you can see that we have simulated different damages, and based on the data that we have applied wavelet transformation, and you can see that the method or the proposed method have successfully identified or the tracked the decrease in the frequency in the data. So which is really nice to see. These are basically different structural modes, and each of the modes clearly show that there is a decrease in the frequency, which is not possible in traditional methods. Now, so far we talked about damages, but cracks are another important parameters for damage evaluations. So for example, if we don't detect cracks at the early stages, as you know, because of the crack, what happens? There may be leakage of the moisture, and because of that, we may see the corrosion, right? So we should not just look at the big damages in the structures. We should also look at the minor damages like cracks. And the machine learning methods that I have presented so far, they are good for identifying the bigger, like the larger damages, but they are not suitable for minor damages. And that's why I need to rely on deep learning techniques or convolutional neural network, as I briefly mentioned before. So this is the context of deep learning techniques where we are successful in identifying the minor cracks. Okay, and this picture or this slide shows a sample masonry wall where the damages or the cracks are simulated during the test, and we have developed convolutional neural network based approaches. So this is basically a typical network that we develop, and based on that, we have been successful in identifying the cracks automatically. So this is totally automated process. We collect a lot of images that contains the cracks or uncracks, and then we train the model using the proposed configuration of CNN, and then we try to identify the actual cracks in the new or test data sets. Now, when there are images, that is relatively easier because from the camera we can get the images and videos. But again, getting large amount of images is not that easy. Probably you know, if you want to identify cracks in the pavements or the potholes, then you need to take a lot of images because the deep learning algorithm that I just said in my previous slide, it actually needs a lot of images. If you have very few images, like 50 or 100 images, that may not work. So you may need 5,000 or 10,000 images such that you can have a proper training, and then you can go for testing. So to eliminate that problem, recently we came across vibration-based damage localization using some advanced technique like 1D CNN. So here you can see that I'm not using the images, rather I'm using the vibration data. So this is some vibration data that are discretized into multiple windows, and then we developed some deep learning technique for identifying the localized damages from the vibration data. So that's another way we solve this problem. So for example, this is some of the results. As you can see, this is a bridge in Switzerland, and this is actually one of the benchmark data that is available online. So what we did is actually we considered two different cases. In one case, we have 20 millimeter of pier settlements. In another case here, we have 90 millimeter of pier settlement. So for 90 millimeter of pier settlement, So here the y-axis is basically the indicator. As you can see, when we have basically the peer settlement, it shows, the indicator shows these are, they exceeded the threshold, whereas this is the data for the undamaged peer. So for the undamaged peers, you can see the indicators are well below the threshold, so which means that this peer is not damaged. So you can see this is some simple way we can say that what's the advantage of this kind of automated process, because we can clearly separate the damaged or undamaged structures. This is another way we can show what's the advantage of SHM. So in this particular research, what we did is basically we developed some computer models to have some sort of connection between the actual structure with the computer models, such that we can connect them using building information modeling. So this is called bridge information modeling. So let's say this is the actual sensor located in the bridge, and then we have a computer model where we simulated the virtual sensor. So this is like same as the online kind of thing. And now once we collect the data, we connect that data with this virtual sensor. So what's the advantage? The advantage is in future, if you want to see how this bridge is doing, we can just click on it and we should be able to see what is the condition like of the entire bridge online. So this kind of tools are extremely beneficial because they can give nice visualization. Because if you put sensor, you'll get a lot of data. So if you don't have this visualization, the bridge owners, they may not be feeling comfortable using the data that we collected. So this kind of visualization will help, and it can help us to provide a lot of information about the condition of the structure at different stages of their life. Okay, so with that, maybe I'll quickly go through some of the full-scale studies that we have done, followed by the summary. So these are some of the examples that we have implemented. For example, this is airport control tower in Toronto Airport. We have actually implemented our algorithm for tune mass damper that I discussed a few slides ago. So this is basically a tune mass damper we came up with, and this was successfully designed using the proposed algorithm, and which was installed in this control tower in Toronto Airport. We implemented our algorithms in different bridges across the world. For example, this is in Montreal. This bridge is located in Germany. This is in Ireland. And these bridges, actually, we implemented our algorithms to monitor the bridges and identify the damages. This is one of the high-rise building in UCLA, which is in US. We use that to check our algorithm with limited sensors. This is one of the bridge in Thunder Bay that we monitored, and we performed the serviceability assessment using the proposed algorithm that based on machine learning and deep learning. This is one of the nice full-scale or study at the experimental level, where we actually show how we can control the vibration of the structures, and also how we can store the energy. So let's say the structure is moving, how we can extract that mechanical energy into electrical energy. So we did some sort of proof of concept study with this work. These are some additional full-scale study. As you can see, this is a small-scale bridge where we have shown how we can identify the fatigue crack from the strain gauge data. This is one of the concrete dam where we implemented our algorithms for their serviceability assessment. This is one of the examples for identifying the leakage in the water pipelines. Again, we implemented our algorithms to identify the leakage or the cracks there. This is one of the dam located in close to London, Ontario. Recently, we put acoustic emission sensors. So this is a schematic of that, and these are the acoustic emission sensors. As you can see, And these sensors are basically they can provide a lot of information about the cracks. And we put these 3 sensors in the wall of the dam, and it shows very clearly where is the damage, as you can see in this result. So typically in some of the locations there were cracks and it shows high amplitude, and that's how we detected the cracks at different locations. So this again, it shows how these algorithms are effective. And finally, this slide shows some of the maintenance strategies that we have taken. So here you can see this is a baggage handling system in Toronto Airport. And basically, this kind of baggage handling systems, it is not just in Toronto, it's in all airport in the world. So they are responsible for moving our baggages from one terminal to another terminal or to the aircraft. And basically if there is a failure in any of the baggages, there will be delay, right? So the airport authority, they would like to make sure there is no delay or there is no breakdown, because if there is a breakdown, there will be delay in the flight and so on. So we actually came up with bearing diagnostic methods such that we can identify the failures on time, and we can stop this kind of breakdown failure. So for that we came up with different machine diagnostic techniques. So as you can see here, this kind of techniques, if you know, the advantage is you don't have to limit your expertise only in civil. You can also explore that in mechanical systems as well. So this is another example which is in mine. And here basically they have automated material handling systems. So this is in a mine in one of the largest mine in North America, which is a palladium mine. And they have long passages like that, which actually transfer the material from one place to another place. And we came up with different statistical analysis using hidden Markov models to identify if we can detect the damages or find out the remaining useful life such that we can fix them before the catastrophe happens. Okay, so far I think we mentioned about what are the advantages and what are the applications. So let me conclude my presentation with some summary. As you can see here, the system ID methods, they are extremely powerful. And my objective of this presentation was to just to show you a quick idea about what they can do without going into the details. I think for undergraduate level, it is really difficult for you to go into the details of this technique. But overall, you can see there is some development in signal processing, but still all of our applications are civil engineering applications. So students need a deeper understanding about the structures or the structural analysis, structural design to implement these algorithms in a proper way. And you can also see SHM is one of the multidisciplinary research. Probably now you understand it involves signal processing, computing, software developments in this area as well. So it's actually excellent field of research where you can use latest technology in civil engineering domain. And it involves not only just analytical studies, you need to do a lot of experiments and full scale. So that's the advantage. As a future researcher, you don't have to limit yourself just on the analytics side. And nowadays we are integrating artificial intelligence and scientific computing. So for students doing graduate studies in this area will be highly beneficial, because once you graduate, there will be a lot of value of this research. And you can see that next generation monitoring, these are highly recommended, not only in North America, worldwide, because with that, we should be able to monitor the critical aging systems, and we can failure catastrophic, like we can mitigate the failures that we can see in different places. And that way we can have better structures, and we can maintain the safety for our citizens. Okay, so with that, I'll conclude. And before that, maybe I'll quickly acknowledge my students, my team, my past trainees of my team, also my collaborator from Western, Waterloo, and Lakehead. I would also like to thank my collaborators from different countries. Also, I'd like to acknowledge my granting organizations like NSERC, MyTax, and Western Research, and also my industry partners like WSP, CMDC, NAP, and conservation authorities in Canada. With that, I'd like to thank all of you for your attendance and listening to my presentation during this pandemic situation.
For sharing and wisdom with us. Now we'll take the questions. So the first question will be by Professor Shyamal.
Yeah. First of all, I express my thanks to Professor Sadhu for giving such excellent presentations on topic of structural health monitoring and
thank you so much
assessments of structures.
Yep.
Okay, sir. Actually, we are very privileged to have you in this talk, CIVINAR, and especially I am very interested because my research topic is almost similar to you.
Yep.
So I have some one or two questions.
Yes.
I have to ask from you. Actually, actually I couldn't understand what is the visual sensor. Is it it is operated by some software?
I think it was a virtual sensor. And yeah, so the virtual sensor is something like which is not directly installed in the bridge, because that's what we say as physical sensor. Virtual sensor is, let's say we develop a Webbit model. Webbit is a tool in Autodesk. So we can develop a bridge model there, and we can assign some node as a sensor, and we can program it, and we can connect that node with the actual sensor where we are collecting data. So what happens, let's say in November we are collecting data, then again after 6 months we are collecting another data, let's say in June or July. So what happened, whatever data we collected from the physical sensor, in the computer model, that data would be associated. So it would be like a very systematic way to visualize the data. So suppose a bridge engineer, they look at the model into let's say next year in December. So they can click and they can select, let's say in November what was the quality, or in June what was the bridge response. So they can just click on the computer model and they can see what was the condition, whether there is any change in the frequency or not, directly from the data itself, rather than saving the data in multiple folders and again perform the analysis. So it is all about the visualization.
Okay. And one more question is that in the problem of damage detection of bridge structures, so what was the measurement? I mean, is it natural frequencies and mode shapes or accelerations?
Yeah, the measurement was basically the acceleration. And we actually, when we use the machine learning methods, we use the blind source separation, where we had to identify the frequency, damping, or mode shapes. Whereas when you use deep learning methods, we don't have to go into the modal parameters. Rather, we directly use some sort of indicator, as you may see in my results. So we use different indicators instead of going into the modal parameters.
Okay. So that is the advantage of deep learning method.
Yes. So in the deep learning, there are multiple advantages. The first advantage is you basically don't have to depend on multiple sensors. You can use a single sensor, and you can still you should be able to identify the severity of the damage or something like that. And at the same time, you don't have to rely on the features, because the features are automatically selected by the algorithm itself. So for example, in machine learning methods, you need to look for the frequency, damping, or mode shapes that involves multiple sensor, whereas in deep learning, uh, you don't have to select a particular feature. Rather, the algorithm can identify the inherent feature by itself. So this is actually good for the bridge engineers and owners if they have lack of knowledge in terms of correct feature selection. But at the same time, there are some limitations also, because you need to have a huge amount of data, because deep learning algorithms, they are based on the training of large data. So if you don't have large number of samples, the accuracy will be affected.
And sir, what is about means noise filtering? Means is any particular type of filtering technique is used in this?
Yeah, so definitely noise is always a secondary issue. But what we try to do is we try to select our sensors, for example, the frequency range or sensitivity, such a way that the noise is mitigated during the data collection stage, rather than taking it and pre-process the data before the algorithm. So we try to use the sensor very cautiously. But having said that, noise may be still there. But some of the algorithms that we have developed so far, they have actually good noise separation capability. For example, in one technique we used wavelet, and there we have used wavelet packet transform. So wavelet packet, the advantage is they can separate the noise automatically, so we don't have to do too much external noise separation.
Okay. Okay. Once again, I thank you from myself because this is my topic of interest, and I was very delighted to have your talk. Okay.
Yeah, you are most welcome.
Okay. Thank you. So students, you
And
can ask
now,
questions now.
now we'll take some questions from the audience.
Yes.
So the first question is by Abhishek, which is, should a heritage monument which has become fragile over the age be demolished and disposed in a safe way, or is there any other way to keep them safe for civilians?
Yeah, this is a very nice question. And when we say heritage monument, so our purpose would be to keep it as long as possible, because there is some heritage value, and we would like to show our citizen that this kind of monuments have been constructed maybe 200 years ago, right? So if we just demolish, uh, then it may not have that heritage value at all. So that's the beauty of SHM, because with SHM we should be able to tell whether there is significant probability of failure in recent years or not. So we can make those kind of decisions, and if we see that the monument may have significant probability of failure soon, maybe we can take the decision for demolishing. But at the same time, if the data shows okay, it is still acceptable, the inclination of the tower is still okay, it's not that critical, maybe we can keep it for another 5 or 10 years, and then we can revisit or re-instrument the monument again, and maybe we'll see what's the condition. So especially I would say for the critical structure, we need to increase the frequency of the monitoring, such that every year or twice a year we can monitor them, and we can see whether there is a drastic change in the properties of the structure, for example frequency, or the mode shapes, or maybe other indicators. And that way you can get a valuable information whether we need to do the demolishing, or just like we retain it for next few years. So you can make those kind of decisions, and that's the advantage of SHM, without making a blind decision about just demolition.
Okay, so the next question is that whether there is a difference between assessment of structure on land and the structures underwater using sensors.
Yeah, that's, I think, another good question. So to me, the media may have some effect, but we have to carefully select the sensor. That's the only thing. So if you think about a structure, let's say there is a structure in air and there is a structure in water. So the only difference would be there would be some sort of fluid structure interaction. So that we need to take into account during our monitoring stage, and we may have to select a couple of high sensitive sensors such that we don't take into account of the fluid structure interaction. And even if it is there, we need to develop some methodology to separate that before we identify the structural parameters. So that's, again, it's definitely a challenge, and especially for the offshore structures where let's say the piles or the piers, they are located below the water level, and we need to, if we want to detect the damage there, we need to look into the soil structure interaction or fluid structure interaction. So it involves some computer modeling of the structure to understand what's the extent of fluid structure interaction, and based on that we develop newer techniques to solve that problem.
So, would you like to take another question?
Yeah, sure. And I
Okay,
think I can actually get as much as question you have, and until all the students are okay, I can proceed.
sure,
That's
sir.
fine.
So, the last question is, what is the scope of research internship at Western University, Ontario? And basically, what qualities do you look for while taking interns?
um, so basically I can convey the message in terms of my team first. So in if you are interested in my team, I would say, as you can see, my area is structural engineering and structural monitoring. So typically I look at whether the students have some background in structural dynamics, or they have some workable knowledge in MATLAB. So that these are the two things I usually look for. And at the same time, sometimes, because usually we receive a lot of students or the applicants for graduate studies, and we see a lot of students, they take some additional courses like machine learning techniques. Like nowadays, as you know, a lot of online courses are there. These are free, and if you take those courses, you will be a little bit advanced in that area before you start your graduate studies or internship. So those kind of things are beneficial. So that's kind of things I look for the internship. In other teams or other faculty members at Western, they always look for, as me, like they always look for whether you have solid understanding in your undergraduate courses. So make sure you maintain a good scores in your courses. So that is highly recommended, because when any of you apply, the only thing that we look is basically your transcript. So that's the first thing. So make sure you maintain good grades. This is where you can differentiate from others, and that's the only way as an undergraduate student for internship. I think we evaluate, but for graduate students, sometimes, let's say for PhD or for masters, we also look for whether you have any kind of publications or not. At least one publication in master should be uh, really valuable to get the graduate student position, because that way it will not only improve your profile, also it will help you to get multiple scholarship when you come to Western.
With this, we have addressed all the questions. Thank you, sir, for addressing the
Okay.
questions patiently from our inquisitive audience. Now, I would invite Mr. Abhishek Abraham, member of organizing team of CIVINAR organizing committee, to deliver the vote of thanks.
Hello everyone. I hope I am audible to everyone.
Yes, you are.
I think you are muted because I can see
Abhishek,
your
you are mute.
Hello, am I audible now?
Yes.
Okay. Hello everyone. Myself Abhishek Abraham. I am second year undergraduate from the Department of Civil Engineering. I'm one of the organizing member of this event seminar. Let me start by saying how grateful we are towards Professor Ayan Sadhu for taking his valuable time and efforts to deliver this webinar on failure assessments of structure. His contribution in the field of structural engineering is commendable. He proves and demonstrates how engineers can leave their marks in a variety of fields with their innovations. I am sure everything you told us today will be of great use to us someday. I would also like to thank Professor Shyamal, Professor of Civil Engineering of NITR, for gracing the event with his presence. I would like to thank NITR SAC for giving us this chance of constant encouragement to do such events with the help us grow and development. And of course, the webinar wouldn't be complete without its lovely audience. Thus, I would like to thank you all for attending and making it a success. Last but not the least, I thank the organizing team for this event who put their tireless hours into making this event possible and seeing it through. Thank you all for turning up for the session. We hope all of you are keeping safe and doing well. We will have more such interesting sessions in the upcoming days, so stay tuned. The video link of the previous sessions and the sessions is provided in the description. You can go through that, and don't forget to subscribe our channel. Also, to follow our Instagram and Facebook pages, and kindly check our website cestnitia.tech for more updates. Take care and see you all again next time. Bye-bye.
Okay, thanks all of you again for this invitation. It was my pleasure to have this presentation in front of all of you. I hope this talk was useful. And again, if you have any question or if you have any kind of questions related to graduate studies or internship, please feel free to email me. I think you have my email ID in the video. And thanks again, all of you. Take care and stay safe.